everybody, we're going to talk about blood pressure regulation and how it deals with the physiology of blood flow. So this is actually one of our toughest topics that we've covered so far in terms of physiology. I do encourage you to go back and watch this video again as many times as you need. I'm on page 52 of your course pack. We're near the bottom of the page. They are talking about the physiology of circulation. So blood pressure is defined as a force. It is the push or pressure of blood plasma. Remember, that's the fluid part of the blood that exerts against the inner walls of the blood vessels. Blood pressure is the force that keeps blood circulating continuously between heartbeats. Keep in mind, we talked about blood pressure being measured in millimeters. That's mm mercury, and that's of course represented by Hg. So blood pressure is felt throughout our vessels, especially through the arteries and arterioles, and then we have no discernible pulse in our veins or venules. So when we're talking about blood pressure, we experience that in our arteries and our arterioles. Now in this picture, you're looking at blood pressure, and you'll notice there's an oscillation in the aorta, elastic arteries, muscular arteries, and then it starts to become pretty much a stream of blood pressure in the arterioles. We see pulsations between systolic pressure and diastolic pressure in the aorta, elastic arteries, and muscular arteries. That's where we expect to feel a pulse. We feel less of one in arterioles, and then by the time you reach capillaries, venules, veins, and vena cava, you no longer feel a pulsation because there's just a steady stream of blood flow through those vessels. So the numbers here should look familiar. In the aorta, we have a systolic pressure typically around 120, a diastolic pressure typically around 80. So you're seeing that pulsation from systolic to diastolic pressure as we travel through the arteries close to the heart. Those would be our elastic arteries. And then, of course, the muscular arteries, which are the ones carrying blood to our particular body parts. You'll notice that when we reach the arterioles, follow this line here in the middle. There's a very steep drop-off as we reach the arterioles. In fact, when we enter the arterioles, blood pressure is around 80, and when we exit, we're going here into the mid-30s. So that is where we see the steepest decline in blood pressure. Aorta has the highest pressure, arterioles have the steepest decline. There's a couple of reasons for that. One, arterioles are smaller in diameter than arteries. Okay, so when you've got a smaller diameter, that's going to affect how the pressure of the blood can flow through. So the pressure tends to drop when we reach a vessel of a smaller diameter. Another thing is the distance from the heart. We know that arterioles are farther from the heart, so the force of the heart contracting is less felt by these vessels farther away. Okay, so that's really why we tend to see a great drop-off in pressure in those arterioles. You'll notice the capillaries have some pressure, mid-30s to the mid-teens. The venules, vena cava, they tend to drop off towards 0 by the time we reach down here into the SVC and IVC. So that's why we need aids and assists like respiratory pump, skeletal muscle pump, and valves in those large veins. We've talked about this picture before back in the heart chapter. Just want to point out that normal blood pressure tends to range between 80 and 120. We notice that low blood pressure is less than 80 systolic or 60 diastolic, while we see hypertension stage 1 begin at 140 over 90. You may remember cardiac output from our discussion back in the heart chapter. CO stands for cardiac output. What does HR stand for? That's heart rate, and SV, that's stroke volume. All right, so you may recall that cardiac output was approximately equal to 75 beats per minute times 70 milliliters of blood. You may recall that gave us a cardiac output of 5.25 liters per minute. Okay, so on average, we said that there was about 5 liters of blood circulated through the body by each minute. Cardiac output is, of course, an influence for blood pressure as well. So we know that cardiac output here plays a role in blood pressure regulation. PR is not Puerto Rico, it is peripheral resistance, and we'll talk about that in just a moment as well. blood pressure does rely on cardiac output, which is, of course, dependent upon heart rate and stroke volume. So let's talk about cardiac output. Cardiac output is the main determinant of blood pressure. This is the #1 influence on blood pressure. Okay, so let's talk about cardiac output. We know on average we're looking at 5 liters of blood circulated by the body in a minute's time. When you studied cardiac output in previous chapters, we talked about blood's composition. We know that blood is around 55% blood plasma. So what's the main component of blood plasma? That's water. Okay, and the other 45% of your blood, that's blood cells, and in fact that's mostly red blood cells. So when we're talking about cardiac output, we're looking at your hydration status, because that's the water in your bloodstream, and we're looking at how much of your blood is composed of red blood cells. Keep in mind, less than 1% of your blood is contributed by your white blood cells and your platelets. Okay, so if you have too many or too few white blood cells or platelets, they have very little influence over your cardiac output and very little impact on your blood pressure. What has the greatest impact? Well, that's how much water you're circulating, and that's how many red blood cells you've got. And so we're looking at this ratio, slightly more plasma than blood cells that we're circulating. That's what we're looking at for cardiac output. Let's talk about peripheral resistance. Peripheral resistance comes in 3 forms. In other words, peripheral resistance is anything that provides resistance to blood flow. If you provide resistance to blood flow, you're going to have an influence over slowing down that blood flow. So we're going to talk about viscosity, which is the thickness of the blood, vessel length, and vessel diameter. Let's talk blood viscosity first. Okay, so I'm going to use an analogy here of drinking a milkshake. Milkshakes may be really thick. We would say it's a viscous or a thick milkshake. A thin milkshake we would say is more watery or runny. It's less viscous. So there's some things that can influence how thick your blood is. One would be how much fluid you're circulating. If you have less fluid, your blood would be thicker and more viscous. If you have more fluid, however, your blood would be thinner and it would be less viscous. The more viscous your blood is, the higher your blood pressure goes to circulate that thick blood. The less viscous your blood is, the lower your blood pressure goes. Now, we also know that 45% of your blood is composed of blood cells. So what is polycythemia? That is increased red blood cells. Well, we know that that kind of alters the ratio, and that means by nature we would have less water in your bloodstream. Okay, so the more blood cells you've got, the harder your heart has to pump to circulate those blood cells. So we're going to expect to see an increase in your blood pressure for a case of polycythemia. Normal blood, of course, means that we have the ratio right, the right amount of red blood cells to water. Anemia, on the other hand, might mean that we're looking at a decrease in viscosity of your blood. Okay, so viscosity is dependent upon 2 things. They are how much water you have in your blood plasma and how many red blood cells you have to circulate. Anything that alters your water content or your red blood cell population can either increase your pressure or decrease your pressure. Let's talk about vessel length. If you're given a milkshake to drink and you're handed a regular drinking straw versus a garden hose, and even if the diameter is the same, why would you pick the drinking straw? Well, it's shorter, right? Garden hose, it's 50 feet long. You'd have to provide an awful lot of suction power to pull that milkshake through a vessel or a tube of that length. So the more weight we carry, the more vessels the longer the vessels have to be to serve that tissue. That's why they say that with greater weight comes higher blood pressure. And that's also why we're encouraged to lose weight, because the weight loss will then reduce the amount of vessel length that we have in the body. So the longer the vessels, the higher the blood pressure, and the shorter the vessels we've got, or the length there, then the less the pressure is going to be. So the heart has to work harder if you have more miles of vessel to serve. Finally, this is the only thing that your brain can control through nervous system activity, and that's vessel diameter. Let's say that we want to either increase blood flow to some muscles or decrease blood flow. This might sound familiar, kind of like how parasympathetic and sympathetic nervous system stimulation controls blood flow to various parts of our bodies. So vessel diameter can be controlled. We can either increase the diameter, and that's called vasodilation. Okay, that's increased diameter. Or we can decrease the diameter, and that's what we call vasoconstriction. Okay, now, if you decrease the diameter, you've increased the resistance to flow. And what impact do you think vasoconstriction will have on blood pressure? That will increase blood pressure. Okay, so if you are tightened up, you're stressed out, your blood pressure goes up, those vessels are constricting. If you take a deep breath and you relax, the vessel diameter increases, and the blood pressure will then in turn decrease. Okay, so that's why they say, like, deep breathing exercises, putting your mind in a frame of being relaxed and not stressed out will help to increase the diameter and decrease that blood pressure. Okay, so let me turn your page with you and go on over to page 54. There is a portion of your brain that controls vessel diameter, and it is called the vasomotor center. If you break this word down, vaso, of course, means vessel, motor, of course, meaning muscle control. And so this particular portion of your brain can either stimulate and constrict those vessels or stop stimulating and relax those vessels. Now, earlier, I did mention to you that there is no parasympathetic control or parasympathetic innervation going to your vessels. Okay, so that's important to keep in mind. There is no parasympathetic innervation to vessels, so either we increase sympathetic stimulation, which promotes vasoconstriction, or we decrease sympathetic stimulation, which promotes muscle relaxation. Okay, so here, let's take a look. Vasoconstriction, was that increased sympathetic stimulation or decreased sympathetic stimulation? Well, in order to cause our vessels to constrict, you have to have increased sympathetic stimulation. And just to remind us what that means, that's epinephrine and its buddy hormone, norepinephrine. So those two will cause vessels to constrict. Now, vasodilation occurs with decreased sympathetic stimulation. So that means there's less epinephrine, and that means there's less norepinephrine. So let me remind you here, great thing to remember, there's no what? There's no parasympathetic innervation to your vessels. So all you can do is this. Let me give you an example. If you're driving a car and the brakes have failed, you have two options. You either step on the gas or you take your foot off the gas and you coast until your car comes to a stop. That's exactly what happens with blood vessels. You either step on the gas, which is increasing sympathetic stimulation, or you take your foot off until your car coasts to a stop. That's decreasing sympathetic stimulation. We have no way to put the brakes on vasoconstriction. You have to wait for your vessels to eventually relax. That's why when you're stressed, it is so hard to unwind, because you're having to wait for that sympathetic stimulation to stop keeping your vessels in that constricted state. So blood pressure can be controlled by your state of mind. That's what we call our higher brain centers. That's your conscious control over your nervous system. If you're really stressed out, if you're in a relaxed state of mind, whichever you are, that neural control can control your vessel's diameter. There's also chemical control, hormonal control. We'll talk more about those in the coming pages. But there's a lot of feedback that occurs here through receptors, things like baroreceptors and chemoreceptors that help us to maintain our proper blood pressure. All right, so here's a summary for the vasomotor center. It is in the medulla oblongata of the brain. It is part of a larger center called the cardiovascular center that also includes the cardiac center. The cardiac center specifically controls the heart rate, while the vasomotor center portion controls vessel diameter. These, of course, are part of the sympathetic nervous system. The sympathetic nervous system works with epinephrine and norepinephrine. And keep in mind, there is no parasympathetic innervation to vessels. So, in other words, we have no brakes on causing vessels to constrict. They either constrict through sympathetic stimulation or they dilate through the lack of sympathetic stimulation. So the vasomotor center controls blood vessel diameter. We cannot control vessel length or viscosity. The only type of peripheral resistance we can control is vessel diameter, especially in those smaller arterioles. If the vasomotor center is stimulated, then the vessel constricts. If we stop stimulating the vasomotor center, then what happens to the vessel? It relaxes. Okay, so let's talk about baroreceptors and chemoreceptors for just a moment. We know your brain state of mind can influence the vasomotor center, but a lot of the influence is outside of your control. There are baroreceptors that detect pressure changes in your carotid arteries and your aortic arch, and that information is then fed into your vasomotor center. There are also chemoreceptors, and like their name implies, they detect chemical changes in your bloodstream and likewise feed that back into your vasomotor center as well. Specifically, chemoreceptors detect oxygen changes in your bloodstream, carbon dioxide changes, and hydrogen ion level changes in your bloodstream. Keep in mind, hydrogen ions contribute to the pH of your blood. So it is in the common carotid arteries and aortic arch that we have these receptors buried in the wall. So let's just use this as an example of a baroreceptor reflex. This is a negative feedback loop, and as you know, negative feedback loops are set to control a set value. So we're looking at a narrow set of ranges in the body. All right, so keep in mind, normal blood pressure, we said, is somewhere between systolic and diastolic, somewhere around 110 or 120 over 70 or 80. So we'll just use those as our values. And let's say that the baroreceptors here detect changes in pressure. Let's say that we have pressure that's too high. Okay, let's say the blood pressure is 180 over 120. Okay, so that information is then carried by way of nerves like the glossopharyngeal to the medulla oblongata. The medulla oblongata then receives this information. Because it's part of your central nervous system, it makes the decision on how to handle this. The medulla oblongata says, maybe we should fix this problem, so there's a twofold solution. Okay, so the cardiovascular center has two parts. Okay, so the way to decrease this blood pressure is twofold. One is to increase parasympathetic stimulation to your heart. Ah, did you catch that? There is parasympathetic innervation to your heart. There is none, however, to your blood vessels. So the vagus nerve here is part of your parasympathetic nervous system. Okay, so it will take a message to your heart, and we will decrease your heart rate through the firing rate of that SA node. So parasympathetic, we're going to increase that stimulation to the heart. We'll tell that vagus nerve there to decrease that SA node's firing rate. Okay, so the heart rate will slow down. All right, keep in mind the cardiovascular center has two portions. It's a cardiac center that controls the heart rate, and it's also a vasomotor center. So the second message has to go out to our vessels. What do we want our vessels to do? Well, we want them to dilate. That's how we lower the blood pressure. So how do we tell our vessels to dilate? We slow sympathetic stimulation, and of course vessels dilate and BP will fall. Now keep in mind there is no parasympathetic innervation to our vessels, so you can't automatically cause them to relax by sending those nerves impulses over the parasympathetic pathway. The only thing you can do is just wait for those vessels to dilate by stopping sympathetic stimulation to those vessels. Okay, so if this is not really clear yet, it's okay. We're going to talk through several examples so that you can get a hang of this process. Here's another picture of how baroreceptors are situated in the aortic arch. They do carry information back to the brainstem, and of course that brainstem is going to receive that information and make decisions, and the message that comes back is twofold. The cardiovascular center here sends information to the cardiac center, or from the cardiac center to the heart, and also from the vasomotor center to these vessels. Okay, so the first step here is baroreceptors send information to the cardiovascular center here in the brain. The cardiovascular center is two parts. It's a cardiac center that sends information here, so we'll call that 2A, to the heart, and 2B, that information goes from the vasomotor center to our vessels, changing their diameter. And of course, that's going to be kind of a 1-2 punch in controlling heart rate and blood pressure. Let me talk to you about chemoreceptors for just a moment. There are chemoreceptors, as you can see here, in the medulla oblongata. There are also chemoreceptors that are found in your common carotid arteries and aortic arch. So these chemoreceptors are looking at oxygen levels in the bloodstream, carbon dioxide levels, and hydrogen ion concentration. So when we're talking about chemoreceptors, keep in mind that they are detecting three things: O2 levels, CO2 levels, and hydrogen ion levels. Hydrogen ion plays a direct role in pH. So let me walk you through an example of high blood pressure. High blood pressure might be coming from increased blood viscosity, and that would lead to an increase in blood pressure. Because it's a blood pressure issue, that's why a baroreceptor is the one to pick up on that high pressure. Where are baroreceptors located? They're found in common carotid arteries, and where else? In the aorta. Okay, so these receptors now send a nerve impulse to your brain. Where specifically? Medulla oblongata, right? And there's a specific center here called the cardiovascular center. Now, the only portion of this story here where control happens is in the medulla. The medulla makes a decision to reduce sympathetic stimulation to the heart and the vessels. What does that do? Well, that turns on the vagus nerve. The vagus nerve releases acetylcholine onto the heart, and the heart rate slows. But this is a 1-2 punch, so the second part of the story is this. We're going to increase sympathetic stimulation to your heart, and that, of course, is going to make the heart rate slow further. Keep in mind there's no parasympathetic stimulation to vessels, so the only thing we can do here is decrease sympathetic stimulation to vessels and watch them dilate over time. So unfortunately, there's no magic button here that causes vessels to dilate. You just have to wait for them to eventually open up their diameter and watch the BP fall. Let's talk about low blood pressure. Low blood pressure could come from, say, not enough blood for one case. And again, low blood pressure is picked up on baroreceptors. Where are baroreceptors found? They're found in common carotid arteries, and where else? In the aorta, okay? And this time, because pressure is too low, the cardiovascular center portion of your medulla will increase sympathetic stimulation to both heart and vessels and decrease parasympathetic stimulation to your heart. Keep in mind, there is none going to your vessels, right? So now we see more epinephrine and norepinephrine heading to the heart. The SA node fires more quickly, heart rate increases. This is a 1-2 punch, so the vessels also constrict. We see blood pressure increase due to sympathetic stimulation. So keep in mind there's two portions of the cardiovascular center. There is a cardiac center that controls heart rate, and there's a vasomotor center that controls what? It controls vessel diameter. Okay, so let's talk about this term here, alkalosis. Alkalosis is a condition of the blood. That means the blood pH is too high. Okay, so it's too alkaline as opposed to acidosis, which is a state of being too acidic. Now, this means we have too few hydrogen ions. So this time, chemoreceptors pick up on that change in the blood chemistry. They are found in the common carotid arteries, aortic arch, and also in the medulla oblongata. These cardiovascular, or these chemoreceptors notify the cardiovascular center, which in turn makes the decision. Now, there's a lot of stuff tied in here together. The cardiovascular center will then reduce sympathetic stimulation to your heart and increase parasympathetic stimulation, but only to your heart. Keep in mind, none goes to your vessels. Okay, so the vagus nerve is a nerve that travels away from your brain. It innervates your heart and other organs. It will cause acetylcholine to reduce your heart rate. Heart rate slows due to a slowing SA node firing rate. The vessels dilate simply due to a lack of sympathetic stimulation, and in turn, blood pressure will fall. So you're wondering, how does this fix the problem? Well, if your blood circulates more slowly, your breathing rate will also fall, and in turn, you will keep more hydrogen ions that you would have exhaled in your outgoing breath. So ultimately, you will keep more hydrogen ions by keeping carbon dioxide molecules. Part of this story I will have to tell you about when we reach the respiratory system. So some of this stuff, I'm leaving out a little piece of the puzzle here that is actually played by that breathing rate. So this term here, hypercapnia, means too much CO2. So obviously this is the respiratory system that's causing excess CO2 to build up in the bloodstream. And we know that carbon dioxide, oxygen, and hydrogen levels are detected by the chemoreceptors. So chemoreceptors are detecting this, sending messages to your cardiovascular center. So thinking about this, if you've got too much carbon dioxide, you want everything to speed up so you can get it out of your system more quickly. And you do that by increasing sympathetic stimulation and decreasing parasympathetic stimulation to your heart. And we do this using epinephrine and norepinephrine. Heart rate increases, vessels constrict, blood pressure goes up, and of course, one piece of this puzzle we are not including in the conversation is respiratory rate will also increase. All right, so one more example here, hypoxia. Hypoxia means low oxygen levels. Okay, and of course, this is something our respiratory system is helping us manage. So if you have oxygen that's too low, once again, this is a chemoreceptor that picks up on the problem. The cardiovascular center increases sympathetic stimulation to heart and vessels, causing heart rate and blood pressure to increase, and we decrease parasympathetic stimulation to your heart. All right, so what I'm going to do is I'm going to take this and several examples and I'll put it into a different PowerPoint. In the meantime, I encourage you to take the chart on the bottom of page 54 and answer the questions on page 55. And when you are ready, come back to this next video that I'm going to post for you, and I will work through examples for you and I'll give you the answers to page 55.